All right, 3.3, we're looking at derivatives of trigonometric function. Okay, so let's look at the first case. So we look at an example, f of x equals to sine x. So we say f is defined for all real numbers x, all right? And what does that mean? It means that sine x is the sine of the angle whose radian measure is x, all right? So sine x is the sine of the angle of which the radian measure is x, all right? Um, and the same idea applies if we're talking about cos, tan, cosec, and sec. Right? And very important is this statement here at the bottom. It says that all trigonometric functions are continuous at every number in the domain. All right. So take note of that. Every number in the domain. So if I give you a trig function and say, where is it continuous? It depends on the domain of that function that I gave you. All right. Now, also there is some correlation between a trig function and the derivative of a trig function. For example, if you look at the first graph, there is the graph of sine x, and the bottom one is the graph of the derivative of sine x. Now, if you notice it, y prime looks like cos, because remember, if you take the slope at this point, they just get 0. At this point there, you get a 0. At a point like this, you get a turning point, so it's increasing. And so I notice the derivative there looks like cos, all right? Okay, so at this point in time, all of you know that the derivative of sine is cos, but we just want to prove that that is actually true. Because looking at the sketch of f prime, it looks like cos, so we want to see if it is actually true. So we go back to what we're good at doing, which is going back to first principle, all right, using the definition of a derivative. Now, if I use that definition, obviously this is a definition. When I talk of first principle, that's a definition there. So where you see f of x plus h, you're just going to say sine of x plus h minus f of x just means minus sine over h. As usual, we need to try and expand this piece here. Right? What is sine of x plus h? You know, sine of x cos of h plus cos of x sine of h. Those are some of the identity you need to know. All right. And once you do that, you can split. Remember, we say that we can, this everything there, the numerator, the share a common denominator means you can split them out. So I'm grouping this. I group this piece and this piece here. So I have sine x cos h minus sine x over h, and then I have cos x sine h over h. All right. We're going to see why we're doing that grouping. We're doing the grouping because there's something that's common. In the first grouping, sine x is common, and the second one, cos x is common. But now we don't know this. All right. This is where the challenge comes in. These ones, they're very obvious because the limit as h tends to 0 of sine x is just sine x, because you can actually treat x as a constant in this case. All right, x is not changing because h tends to 0, but x is just a constant, so it's not actually changing. So you get sine x, and we also know this limit here, but the problem is these two guys here. So we even gave it a name. We call them the special limit. So anywhere in my test or anywhere you go and they talk of the proof of the special limit, please think about these two guys. All right, so one of those two. All right, but to avoid confusion, if I want you to prove the special limit, I'll tell you which of them. So for now, we're going to start by looking at the proof of this guy. All right, sine h over h. Okay, so we know already that this is sine x and cos x. So let's try and see what we get for those two special limits. Let's start with the first one, which is a limit as theta tends to 0, sine theta over theta is equals to 1. Let's see how this is true. Keep in mind that we got to this answer just on the basis of some numerical and graphical evidence, but we should be able to prove that it is actually equal to 1. And how do we do that? If you look on Blackboard, there is a PDF that I uploaded. It's called Proof of Special Limit. I'm just going to go over that PDF file quickly with everyone so that when I ask you to prove it, you would understand. And be careful because now you're doing online tests, if I ask you to prove this, I might ask you some concept about the proof. So please make sure you understand every piece of the proof, so that if I ask you, okay, why do we make this assumption, then you know why. All right. And obviously, if I ask you to prove this, people will just open their laptop and just start copying word for word, and they smile that they're going to have full marks. So obviously, there are many ways which I can ask you this. Let's look at the proof. Just need to zoom in. If you can see, just zoom in using the device that you have. All right, so figure A shows a sector of a circle with center 0. You can see there's a center 0 there. And center angle theta and radius of 1. All right, so we choose our radius to be 1. Okay, we assume that theta lies between 0 and pi over 2. So our assumption is that theta lies in the first quadrant. All right. And what does that mean if we say theta lies in the first quadrant? It means that that act, so remember the act AB, so I'm just going to this act here. So the act AB is equal to arrow theta. I'm sure everyone has seen this. That is just the definition of radian measure. All right. So the act AB is arrow radius times center angle theta. But take note, this is equal to theta because we say we want our radius to be 1. So 1 times theta is theta. All right. Next step, we say the distance BC. So this distance BC. Let's see if we can change the color quickly. So the distance BC. Let me just get a different color. All right. So this distance here, BC, is equal to what? Remember, sine, the trig function sine relates the opposite and the hypotenuse. So I can say OB, which is a hypotenuse, times sine of theta. Remember, sine of theta is opposite, which is a BC we're looking for, over hypotenuse, which is OB. All right. Therefore, if I make BC the subject, I'm just going to get hypotenuse times sine of theta, which is how we got this. But take note that distance OB, that hypotenuse, is just equals to 1. So 1 times sine theta, we get sine theta. All right. But we say, but the distance BC is smaller than the distance AB. All right, that makes sense, right? Because if you look at this second, let me just complete the triangle there. If you notice it, BA there is the hypotenuse of this little red triangle that I drew. It means it has to be, that distance BA needs to be longer than BC. All right. And also, take note, BA is smaller than the arc AB. So BA is smaller than that blue arc that you see there. All right, AB. And why do we establish this relationship? Because we know that BC is sine of theta. So sine of theta is BC. And we say it's less than AB. So for now, we're not sure exactly what AB is. But we know what this arc AB is, all right? Because we started by saying that arc AB is equal to r theta, which is equal to theta. So therefore, I've shown that sine theta is less than theta. And take note, because theta lies in the first quadrant, obviously it's positive, right? So I can divide all two by theta, and I just have sine theta is less than 1. All right, this first piece there is very important. You should be able to get to that relationship. Sine theta over theta is less than 1. All right, let's keep going. Now let's look at figure B. Figure B, they say it shows that the circumference of a circle is smaller than the length of a circumscribed polygon. All right, and it's true, right? Because look at the circle there in red. It fits inside the polygon, and the polygon has sharp edges, which shows that if I flatten out that polygon, definitely the length there is going to be longer than the circumference of the circle. All right, and using that idea, we can say that the arc AB. So now I'm looking at this second piece here. So the arc AB, which is this piece here, so arc AB is less than, and take note that arc AB is theta, because we've shown that here in the beginning that is equal to theta. So theta, which is equal to arc AB, is less than the distance AE. If you can see from the second diagram, I'll just show you from the first so that you see the relationship. So think about this blue arc. We agree that it is actually less than the combination of these plus this. All right, you can see that And similarly, we see that AE plus EB is also smaller than AE plus ED. Okay, I'm going to show you where ED is coming from. Now, look at this. So this is now AE and this is ED. So we agree that this distance here is longer than that distance AE and EB. And the question is, why do we keep writing this kind of relationship? Because we know that the distance AE plus ED, so this distance here, this one here. So we know that this distance is actually called AD, all right? So it's called AD. And why we're interested in AD is because now we can use, again, our trig ratios. We know that tan of theta is going to be opposite over adjacent, right? So we know that tan of theta is going to be opposite over adjacent. And therefore, you can say that the opposite is just OA times tan of theta. But now, remember that OA is also the radius of my circle, which means it's also equals to 1. So let me just change the color just so that we don't have too many. In fact, let me clear out some of the colors so that you guys can see what I'm talking about in terms of the relationship. Okay, so we're saying that we're looking for this distance here. We're looking for this distance here, AD, right? Okay, we know that is the opposite of this big rectangle there, or big triangle, not rectangle, big triangle. And I know what relates the adjacent and the opposite is tan, all right? So if I say tan of theta is going to be this opposite that I'm looking for, AD, over the adjacent, which is this distance here, which is OA, all right? And OA, if you notice it, is just the radius of the circle. So if you look at it from the second diagram here, OA is a radius, OB is also a radius. And we started by saying that we want our radius to be 1. And using that idea, you see that OA times tan theta just means 1 times tan theta. Then you just get equals to tan theta. All right. So what have we shown? We've shown that theta is less than tan theta, and tan theta is what? Tan theta is sine theta over cos theta. Now, because theta lies in the first quadrant, we know that all the trig functions are positive in the first quadrant. It means that I'm allowed to multiply all through by cos theta, right? Without the inequality sign changing, all right? B1, you only allowed to multiply all through with an inequality in an inequality without changing the sign, only if what you multiply in all through is positive. In this case, we know cos theta is positive. Why? Because we say we want theta to lie in the first quadrant. If you multiply all through, you have theta times cos theta is less than sine theta. And if you divide by theta all through again, you have that cos theta is less than sine theta over theta. But we know, I'm just going to show you where this 1 year is coming from. We saw it from the beginning that, look at this. We saw here that sine theta over theta is less than 1. All right. So if we have cos theta is less than sine theta over theta, it's also true that sine theta over theta is also less than 1. All right. And once you get to this step, you're close to finishing the proof because you think of what? You think of squeeze theorem. Squeeze theorem. Very important. You need squeeze theorem. What does squeeze theorem says? If you take the limit as theta tends to 0 of this cos theta here, you see we get 1. If you take again the limit as theta tends to 0 of the right hand side, which is 1, you see you still get 1. Therefore, you can conclude that the limit as theta tends to 0, from obviously from the positive side, we're coming from the positive side, is of sine theta over theta, which is this middle function here, is also going to be equal to 1. And this is true by what? By this guy here, squeeze theorem. Is true by squeeze theorem. All right. But now the focus here is 0 from the right. So how do you conclude for 0 to the left? You use the fact that this function sine theta over theta is an even function. I'm sure some of you are surprised. Why is this an even function? Why? Because sine theta is an odd function. Theta is an odd function. Odd function divided by odd function gives you what? Even function. All right. So there we go. You have it's an even function. So the right hand and the left hand side limit has to be the same. All right. And in conclusion, it means that the limit as theta tends to 0 of sine theta over theta is equals to 1. All right. Please, I hope you understand this proof. I hope you understand the intermediate means each of these independent steps. Because like I said, I can ask you something in between the lines, somewhere here in the middle or anywhere. You should be able to understand where we got what and why is it written the way it is written. All right. I hope that's clear enough. Let's go back to our slide. There we see how to prove the next spatial limit. I just need to scroll to the correct slide quickly. Yes, we there. Okay, this was what we were trying to prove. Everyone is super happy with the proof. Obviously, the recording will be available for you to go through it. I've already explained all of this. Everyone is happy how we got to the conclusion. Okay, now we want to get a result for this one as well. So we want to see what happens when we take limit as theta tends to 0 of cos theta minus 1 over theta. So this is the other special limit. All right. Now to do this one, there's no need to draw fancy diagrams to try and prove this one. With this one, you just need to play around with the function. So you see here, we multiply top bottom by cos theta plus 1. It looks like the conjugate of this top piece. We just change minus to plus. We multiply top bottom. And if you do that, notice it, you have cos squared minus 1. And then at the bottom, you have theta times cos theta plus 1. And this is equal to, now notice it, sine squared plus cos squared is equals to 1. Therefore, if I say cos squared minus 1, that is just equals to minus sine squared. All right. So if you use that identity, the sine squared plus cos squared is equals to 1. Therefore, if you take 1, if you want cos squared minus 1, and then you take sine squared, the other side is going to be negative. So minus sine squared. And then now the negative there, just take it in front of the limit. Just treat it as a minus 1, which is just a constant. Take it in front of the limit. And now if you notice it, there's two signs at the top. Sine squared means what? Sine times sine. So what I did here is I take one of the sine and I say divided by theta. And then I take the other sign and I say divided by this other function then. All right. So I just split the sign into 2. And using limit laws, I'm allowed to split this limit into 2 as well. I can say minus the limit as theta tends to 0 sine theta over theta. Why do I want to do this? Because I've done the hard work of proving that that limit is equal to 1. So at least I try and manipulate my limit so that I can get an identity that I know already. All right. And all that to be left is this other limit, which we can evaluate. What happens when theta tends to 0? Sine of 0 is 0. Cos of 0 is 1. 0 over 1 plus 1, that is 0 over 2 is 0. 0 times minus 1 is 0. There we go. It means we've shown that this spatial limit is equal to 0. All right. Now we can go back and complete our derivative, right? So here we've already shown that this is equal to 0. Then if we go back to that derivative of sine x, notice that where you see this, it's just going to put 0. And where you see this, you're just going to put 1. 0 times this, all of this is going to fall off. You'll be left with cos x times 1, which is just cos x. Therefore, the derivative of sine is equal to cos. All right. Guys, be careful with my test. If I say differentiate sine, don't show me all the steps of proving the special, all two special limits. No, just go ahead and say derivative of sine is equal to cos. All right. Don't go through this process. If I say show the proof of the special limit, I'll mention which special limit, and so on and so forth. All right. And this applies to this function. So now let's look at this function. Y equals to x squared times sine of x. How do you differentiate this? Guys, it's the product rule. All right. Product rule says that you keep one function, so you can keep the first function fixed, you differentiate the second function, you keep the second function fixed, you differentiate the first function, and boom, you're done. All right. You notice it, x is common on both sides. You can even simplify further by saying that factor out the common x, keep everything as in bracket. All right? If you do that, well done. It means you probably get all your marks for simplification. Now, if we use the same idea that we've done before, when we use that first principle to differentiate sign, if we do that to cos, we'll get the result minus an x. All right? We will not do that whole process. Just know that the derivative of cos is minus an x. And when you're trying to differentiate tan, you need to keep in mind that the derivative of tan is the derivative of sine over cos. Therefore, you can apply the quotient rule. And if you apply the quotient rule, you see that it's equal to sec squared. All right, you're going to get sec squared derivative. And if you know the derivative of sine, the derivative of cos, the derivative of tan, therefore everything else, so this one here, it becomes very easy to get because you just apply quotient rule. Remember, cosec is 1 over sine, sec is 1 over cos, cot is 1 over tan. It becomes easy to differentiate using the quotient rule. All right. And this is a summary. Guys, please make sure you look at this table and you understand the derivative of each of the strict function. Now, let's look at this example. How do I differentiate this? You know it's quotient rule. Quotient rule says that you keep the bottom function. All right. This is, I don't know how many examples now we've done for quotient rule, but you see, come the day of the test, some people will start by keeping the top function fixed and differentiating the bottom. You're going to lose all the marks for no good reason. All right. So quotient rule says start by keeping the bottom function fixed and then differentiate the top function minus, now keep the top function fixed, differentiate the bottom function divided by the bottom function squared. All right. And like I said, as a rule of thumb, please don't square the bottom piece. Just leave this bottom function the way it is. Try and simplify the top one instead as much as possible. And you notice here, the sec is common. That's why we took it out. So sec is common here. We took sec out there. We took another sec here. And then we end up with tan squared minus sec squared. Now, if you remember, this also can be simplified because 1 plus tan squared is equal to sec squared. So when I see sec squared, I can replace it with what? 1 plus tan squared. And if you do that, you just, the tan will cancel out and then you'll be left with minus 1 there. And there we go. This is as simplified as possible because nothing else can cancel out. Then you can stop there. All right. How do we do this example? Guys, this is a very nice example. I know because we've done the spatial limit. When people say limit as x tends to 0 sine of something over something, they'll be quick to say it's equals to 1. All right. The good news is that it's not equals to 1. All right. So this is not the spatial limit. I'll show you why it's not a spatial limit. Because if we say it's a spatial limit, therefore we crazy. 7x is not equal to 4x because there's a difference there. It's not the spatial limit. The spatial limit wants sine of x over x, sine of theta over theta, not sine of 7x over 4x. You see, those numbers don't balance out. First thing you need to do is to try and balance out the numbers so that spatial limit rules can apply. How do I balance it? Notice it. I can come here at the bottom and I say, okay, I want sine 7x over 7x, but how do I do that without changing the original function? I just multiply outside by 7 over 4. Why? Because 7 can still cancel with 7 here at the bottom. There we go, and I have my original function. You see? And it's also true that if I let theta to be 7x, then theta tends to 0 as x tends to 0. Remember, if x tends to 0, 7 times x also tends to 0. All right. Now the limit as x tends to 0 of sine 7x over 4x is going to be what? 7 over 4. Everyone knows where it's coming from when we did this balancing here. Limit as x tends to 0 of sine 7x over 7x. All right. We can take this to the special limit, which is now the limit as theta tends to 0 of sine theta. Remember, we started by letting the 7x to be theta. So sine of 7x will just be sine of theta, and divided by 7x just means divided by theta. And this is the special limit where theta tends to 0, sine theta over theta, which is equal to 1. 1 tends over 4 is over 4. All right. Guys, please don't see this in my test or in my quiz. You quick to say it's equals to 1. No, you must check. You must check this piece that I circled. The 7x is not equal to 4x. So start by balancing that before you think of special limit. All right. Let's keep going. This is another example. Now, please don't do direct substitution, because if you put x equals to 0 there, you get the wrong answer. I'll show you something. If you make x 0, you're going to get 0 times cot, all right, which is going to be 1 over tan is cos over sine, and sine of 0 over 0. And you get something like it's not defined, and so on, all right? That's wrong. The answer there is wrong. Now, always try and simplify. If you see a tan, you see a sec or a cot, write it in terms of the other trigonometric function. For example, cot is cos over sine. You see here, cot is cos over sine. I can manipulate it because we're allowed to leave cos there at the top and take x there at the bottom. All right. I'm so sure some of you are very confused. I'm going to show you why we're allowed to do that. So, for example, if I give you something like this, how do you simplify this? This is the same as, you can change this division here to multiplication by taking the reciprocal of the bottom piece. So you can say A times the reciprocal at the bottom. So it means you're going to get C over B. All right. Now, if you use this idea here, this looks like this. And what I wrote here is actually this. All right. So you now understand why we allow to manipulate it. And why we manipulate it? Because we love to see sine x over x, because it's a special limit. We want to get to the special limit. All right. This step here is just splitting the limit. So take the limit of the top function divided by the limit of the bottom function. What's the limit as x tends to 0? Of course, it's just cos of 0 is 1. So you get 1 divided by special limit. Remember, this bottom one is special limit, which is equals to 1. 1 over 1 is 1. There we go. So you see, if you try to do direct substitution, especially those that are not in class today, they'll be tempted to do direct substitution and they'll get 0 actually for this kind of questions. All right. So if you see a question like this, please manipulate, simplify as much as possible. And this just shows you where trig functions are often very important in life. And that's basically for 3.3. There's no question. We're just going to move straight to 3.4. Like I said, we need to cover both of those in today's class. Is there any question? If there's no question, then we move to the chain rule. All right. This is another interesting section. What is chain rule? Now, to understand why it's important to know the chain rule, every method I've shown you so far, it doesn't work. So all the different, the method of differentiation that you've learned, it cannot help you to differentiate a function that looks like this. All right. So if you try to differentiate, you're going to struggle, right? So you can't actually be able to differentiate a function that looks like that. So the idea is to try and treat such kind of function as a composition of one function with another. For example, I can say, the root is one function f, and x squared plus 1 is another function g. Therefore, I can treat capital F of x as f of g. There we go. You see composition. Now, once you see composition within a function, the first thing that comes to mind is chain rule. All right. I'm just going to show you how we came about the chain rule. Let's look at the theorem here. So what does chain rule say? All right. Theorem say if g is differentiable at x, so g has to be differentiable at x, and f is differentiable at g of x, then the composition capital F equals to f of g, defined by f of x is equals to f of g of x. If you take note, g of x is going inside of f of x. All right. That's what composition means. The right function is going into the left function. All right. So that composition is differentiable at x, and f prime is given by this. All right. How do we get f prime? You start by differentiating the outer function, and then you say times the derivative of the inner function. All right. Using Leibniz notation, if you let y to be f of u, and where u is g of x, if both of those are differentiable functions, they will say dy dx is dy du times du dx. All right. Let's look at a nice example. All right. There's no need for you guys to go through this whole u substitution, please. If I ask you my test, just go straight to that formula there. Start by applying power rule. All right. Square root means to the power of half. all right, is to the power of 1 over 2. So if you apply power rule is going to be half times x squared plus 1 all raised to the power minus half, right? There's a power rule. Minus half is the same as 1 over root. Hence, we get this piece here. And then chain rule says differentiate the inner function, which is x squared plus 1. So you also need to multiply that power rule by the derivative of the inner function. In this case, you get 2x. All right, the derivative of x squared plus 1 is 2x. If you multiply those two, you just get x over square root x squared plus 1. All right. This is just using the Leibniz notation where you let u, but I say methods, there's no need to do all of this. Just do the chain rule directly. Differentiate outer function times the derivative of the inner function, right? Just to save time. Similarly, let's look at example 2 there. If you have to differentiate the first one, what did I say? You differentiate the outer function. The outer function here is sine. You can see sine. What's the derivative of sine? You can see it's cos. So that's the derivative of the outer function. And then you need to multiply that with the derivative of the inner function, which is x squared. What's the derivative of x squared? You can see there's 2x. Therefore, your final answer is just 2x times cos of x squared. Right. Again, if you have to differentiate sine of x squared, you start by applying the power rule. So it becomes 2 times sine of x to the power 1. So that's the outer function. The derivative of the inner function is the inner function is sine. All right. I know some of you asking, how do you know if it's an inner or an outer function? Now, sine squared x is the same as saying sine x all raised to the power 2. All right. Is sine x all raised to the power. Now, the outer function is the power rule of when I look at the raised to the power 2. The inner function in this case is just going to be the sine of x. And you apply the same idea here. You differentiate sine, you multiply that with the derivative of tan of 2x. All right. Okay, I see someone raise their hand up. Is there any question? Okay, I guess the person is gone. Yeah, again, they're just showing you how chain rule is applied. So you have y is a function in terms of u. You can see y is a function in terms of u, but u is a differentiable function in terms of x. So we can differentiate y in terms of u, and then we can multiply the derivative of u in terms of x. All right. So that is chain rule. And the derivative of sine is cos, and then we need to multiply that by du dx. All right. So that is just in general you apply your chain rule. All right. This is now the power rule combined with the chain rule. In fact, that is what we used in the previous example. But in summary, this is what it says. It says if n is any real number and u is equal to g of x, is differentiable. So this piece here is differentiable. Therefore, the derivative with respect to x of u to the power n, you see we start by applying the power rule. So the outer function, and you need to differentiate the inner function, which is the u function itself. All right. Alternatively, if you have g of x to the power n, so any function raised to the power n, you apply the power rule, which is n times g of x to the power n minus 1, multiply that by the derivative of this inner function, which is g of x, and there we go, you have your chain rule. All right. More example, let's look at x cubed minus 1 to the power 100. How do you differentiate? You start by applying the power rule. Power rule becomes 100 times x cubed minus 1 all raised to the power n minus 1, which now becomes 99, times the derivative of the inner function, which is this thing in brackets, so it's x cubed minus 1. If you differentiate that, you have 3x squared. 3x squared times 100 just gives you 300x squared times x cubed minus 1 all raised to the power 99. All right. And here is just showing you that the derivative, how we got to the fact that the derivative of a to the power x is a to the power x times ln of a. Let's look at the proof. You see that a to the power x can be written as a to the power ln of a all raised to the power x. All right. That's the cancellation rule says that e to the power ln of a is equals to a. Therefore, a to the power x, I'm allowed to say that e raised to the power ln of a or raised to the power x. All right. Which is just the same as e to the power ln of a times. So remember, I'll just show you what we did there. If you have a to the power, let's say m, you have a to the power m, and then you raise that to the power n, you're allowed to say that this is just a to the power m times n. All right. So because they're both powers, you're allowed to multiply them. So it's basically what we did here. It's just ln of a times x. All right. Now, what then becomes of the derivative of a to the power x raised plus x? It will be the derivative of e to the power ln of a times x. And the first thing they say, you start by differentiating the e function. Remember, if you differentiate the e function, it stays the same. And then you need to differentiate this power here. All right. So the first thing is it stays the same. And then you need to say times the derivative of ln of a times x. And if you do that, you have e to the power ln of a, or e to the power x times, okay, this is, it looks like a box, but it's actually a dot, it's supposed to be a dot, times ln of a. And cancellation rule applies again. E to the power ln of a is a, so you just have e to the power x times ln of a. All right, there you go. Guys, in my test, I'll not ask you to prove this derivative. This is just for you to understand where this is coming from. All right. Now, if you understand that concept, therefore, if I ask you to differentiate 2 to the power x, you should be able to tell me 2 to the power x times ln of a. All right. What is ln? What is ln of 2? Ln of 2 is just 0.69. All right. Obviously, please don't give me decimals. In your first test, I was a little lenient because some of you don't listen. When I say calculators are not allowed, I saw a lot of people giving me decimal answers. Test 2 will be extremely strict when it comes to decimal values. Guys, calculator are not allowed. It means if you have ln of 2, leave it as ln of 2. All right. Don't give me decimal. All right. This is chain rule again. So if you have y a function of x and x a function of t, then chain rule becomes dy dx, dx dt. If you have y a function of u a function of x a function of t, then chain rule keeps going forever. All right. So it simply means that you can get a composition of the composition of functions. All right. And you don't panic. You always start by differentiate the other function, move one step in, move one step in, and so on and so forth. All right. And this is a very good example. So if I ask you to do this, you start with the other function. So just change the color so that if you understand this, it means you're super cool when it comes to chain rule. You start with the other function. Look, the other function here is sine. So derivative of sine of all of this is just cos. All right. So you see I have cos of 10x. So this is the first piece, derivative of that other function. I move one step in. I say times. Then I need to move one step in. Let me change the color. Yellow. I move to the next function. All right, but the focus is on the cos itself. All right, the focus is on that cos there. Derivative of cos is what? Minus sine. So you say minus, you see there's a minus there. Minus sine of 10x. You say times, you move one step in again. And now we're now in this last function inside there, which is tan. What's the derivative of tan? Sec squared. There we go. You're done. Full math. All right. And then how would you do B? Obviously, you start by applying power rule, and then you can differentiate this everything in bracket using the quotient rule. I'm sure everyone can do that. And then how are you going to differentiate this? Again, step by step, the derivative of e to the power sine 2x will be e to the power sine 2x. Then you move to this function here, sine of 2x. What's the derivative of sine of 2x? It becomes cos of 2x. Then you need to differentiate this 2x itself, which is 2. So you have 2 cos of 2x times e to the power sine of 2x. Now you move to the second function. You have sine of e to the power 2x. What do? Outer function is sine. If I differentiate sine, I have cos. That is my outer function. Times the derivative of everything you see in brackets. What's the derivative of e to the power 2x? It stays e to the power 2x. But you need to also differentiate that power there, which is 2x, which is 2. There you go. All right. So guys, if I ask you this in the test, go step by step. Take your time. Don't hurry. Just take your time. Make sure you have every little piece involved. All right. And that's basically for 3.4. Is there any question from your side? All right, silent Maven is happy. Let me just stop